Hi. I always say hi at the beginning of this. I think it's polite, don't you? Okay. I was thinking about it, and I decided I wanted to say a few more words about the second law of thermodynamics. I want to give you a different spin on it, a different way of thinking about it, and propose a puzzle and then answer it. So the second law of thermodynamics, very obscure and technical thing, defines this concept of entropy, which I said, oh, well, it's a measure of how random the system is, whatever that means. Okay, and I talked about that a bit. And I said that the second law says that assuming that your system is isolated, so neither mass nor energy can enter or leave the system, then the entropy of the system can only increase. It can never decrease. It can be more. The entropy can stay the same, or the entropy could increase, but it can never decrease. Okay. So what does that mean physically? Well, there's a lot of implications, and I certainly can't catalog them all. But let me give you one that's perhaps familiar. To start with, going back to our glass of water example, remember that in its liquid state, the system is highly disordered because the particles are constantly moving around, constantly changing positions, and so the number of possible configurations that are possible for this collection of water molecules is huge, all right? And what I suggested was that this system can never lose entropy, okay? And can never become less random than it is. It might stay at its current level of randomness. It might increase, it might become more random, but it can never become less random. And one implication of that statement is that the glass of water can never get colder, because remember what I discussed with a glass of water that was in the solid state, that was frozen, that was ice. The arrangement of the water molecules was very organized, very low disorder, very low entropy. So a low entropy is strongly correlated with a low temperature. And so the glass of water can never get colder. But of course, that's nonsense. It can get colder. We freeze water all the time. Otherwise, I wouldn't even be talking about it. Yes, but that's not an isolated system. And the second law requires an isolated system. So let's see what's going on. Let's see in a very schematic and highly theoretical way, how does water freeze? And what does it have to do with entropy? Well, here's what I will do. I will build myself. How do I want to do this? I think I'll do this. So I want to build myself a big box. And I'm going to put my glass of water inside of it. And I'm going to separate the top and bottom of the box. In a certain way. I don't know what I'm trying to draw here other than they're just isolated. It's isolating. Anyway, something like that. And the point is that the glass of water is in the lower section, and then I've got something going on in the top section. What do I have going in the top section? Well, I'm going to put, can you see that over there? Yeah, you can. So I'm going to insert over here a tube of some kind that I can use to suck in air. So I'm going to suck air in. This is air. Or it doesn't have to be air, it can be almost any gas, but let's use air because air is familiar. Okay? And then I am going to do something. I'm going to put it inside a second box here. I'm going to suck that air into a second box, and something is going to happen inside this box, and I don't care what it is, but something is going to happen inside this box that causes the air to get colder. Okay, so actually, let me draw the incoming air in, let's say, pink. And we'll say that this air is comparatively warm. So we'll say warm air. And I suck that air in, and that air gets sucked all the way, actually, into my little black box here. And then something happens to the air, and eventually the air gets cooled down, becomes colder, and eventually gets pumped into the bottom section of my box here where the water is. Okay? So what happens now is that the bottom half of my container where the glass of water is filling up with air that's very cold, and in particular, much colder than the water, or to put it a little more specifically, the temperature of the air that is now surrounding my glass of water is colder. The temperature of the air surrounding the glass of water is lower than the temperature of the water itself. That means, remember what temperature is. Temperature is a measure or a proxy for measuring how much thermal energy a substance contains. So since the temperature of the air is lower than the temperature of the water, that's equivalent to saying that the thermal energy of the air is lower than the thermal energy of the water, which is going to result, in ways that I've described before, in a net flow of heat from the water to the air. Well, when the water, which is now no longer an isolated system, when the water loses thermal energy, its temperature drops, and by the way, so does its entropy. So the water gets colder. But the air, as a consequence, inevitably gets hotter. And so what we do is we take the now hotter air and we pump it out. Only now, so actually let me pump it over here, I guess. So the air circulates around the cup, but as it goes, it starts to get warmer because it's stealing heat from the water. So the water is losing heat. The air is gaining heat. It's now hot air. And I'll put another pipe here, and we will pump this hot air out. Okay. So in short, we brought warm air in. We cooled it down through some mechanism, which I don't care about. We made the water cold. The cold air absorbed heat from the water. The water lost heat. The water, therefore, decreased in temperature. The air increased in temperature. We're done with the air. We pump it out and bring fresh stuff in. Okay? And we don't want to recirculate the same air because now the air is hotter than it was when we first brought it in. And so we would actually have to cool it down twice, and that's counterproductive. So we might as well bring in air that isn't quite as hot. Okay. Do this long enough, continually refresh the air inside the bottom container. The water continually loses energy until finally it freezes, at which point its entropy is very low and its temperature is very low. And that's that. Okay, so the glass of water has definitely lost entropy. Delta S is definitely less than 0. But the system is not isolated. And here comes the kicker. you'll notice that having added all this heat to the air, now it's hot air. What that means, another way of saying that the air is hot, of course, its temperature is high, but in addition to that, the air's entropy has now increased, okay? And so the air, as it turned out, gained at least as much entropy as the water lost, and it may be that it gained more because of the process of getting cooled by the refrigerator. So refrigerator, yeah, of course what I'm talking about here is a refrigerator or even a freezer, and you have one of these at your home, right? So this is not a mysterious magical device, everybody's got one, right? So, the air gains a whole bunch of entropy that the glass of water lost, okay? And so if we were to consider our system to be not just the glass of water, but the glass of water plus the air plus the cooling mechanism, a detailed analysis would show that in fact the total entropy of that new system of water plus air plus refrigeration device, that net change of entropy is actually definitely greater than zero. Okay, so but you have to have a system that is isolated, and so that means you have to take into account all of the mass, all of the energy. So not only the mass and energy of the water, but the mass and energy of the air as well, and the mass and energy of even the refrigeration mechanism, which is some sort of a pump or something. Okay, so this is in essence how a refrigerator and how a freezer work. And the second law of thermodynamics certainly does apply as long as you are careful to define your system correctly so that it is in fact isolated. Okay, so that's the general idea. I wanted to get that across to you. Good. And sooner or later we'll talk about gases.